Hello, everybody, and welcome to this month's Astronomy on Tap, once again coming to you live on YouTube. Tonight we have an exciting program, two speakers, Leo and Michelle, talking about different aspects, the astronomical aspects of climate and understanding and appreciating our Earth and our global society. So without further ado, just a little bit of an introduction to those of you who don't know what Astronomy on Tap is all about. It started back in 2013 in New York City, and then quite quickly spread over across the world and is now in currently over 40 locations all the way across the world. Our own history at Astronomy on Tap Leiden, we started in March of 2017, so just over 3 years ago. And we run regular events every last Monday of the month, usually in De Burgt in Leiden, but currently online. So thank you to all of you for joining us. I hope you have an exciting night tonight. So just to introduce who will be online today, I'm Wendy. I'll just be hosting. We have a forum through YouTube, through the chat function of YouTube, for you to be able to interact with us and ask questions to the speakers. So we have a moderator, Marta, who will then ask the questions to the speakers. We also have games, again, set up through Google Forms. That'll happen between the two talks. And we're hosted by Liz, who's doing tech support for us. And our two speakers, Leo and Michelle, I'll introduce later. So once again, do leave your questions for the speakers during the talk. You don't have to wait until the end of the talk. That way we have the set of questions already built up to ask at the end of the speakers' talks. And let us know that you're watching. Let us know where you are. Interact with us on social media. Share your photos of your beer or your food, whatever you're drinking. Yeah, and just interact with us. Let us know where you are. Just on social media, obviously you found the YouTube link. We also have a web URL, Astronomy on Tap Pentanel. We're also on Facebook and Twitter, and also more recently Instagram. If you'd like to get regular news from us, please sign up. It can be found on our website, but you can also send an email to astronomyontapleiden@gmail.com. So very briefly, what's been happening in the astronomy world lately, some exciting new things recently in the news. This came up in the last few days, actually, this amazing picture of the protoplanetary disk, so the swarming disk of gas and dust around a young star. And the amazing thing is that this is actually a real image taken with a telescope on Earth, and the detail that you can see is amazing. And it's thought that this little clump of dust and gas, really bright near the center, is actually the formation site of a new planet, as the spiraling, swirling action of the dust and the gas coming together is actually forming a new planet in this dust disk. Another really exciting thing is that astronomers were looking at this binary system in this stellar system HR 6819. And the motions of the stars really suggest that there's another body in the system, and this body can't be seen, and it has a mass of about 4 times the mass of our sun. So it's clearly a black hole. It's an interesting one. It's not, it's a very quiet one. It's not busy eating anything around it. And this would be the closest known black hole to the Earth. So those are two exciting recent things in the news, but what's up tonight? Tonight we have 2 talks. So we start off with Leo talking about the climate crisis from an astronomical perspective. Then we'll have our quizzes or our games with a short break to give you time to refill your drink or go to the toilet or finalize your quiz answers. Then we'll go on to the second talk by Michelle, which is about the pale blue dot. Stay tuned to what's that about. Then we'll give you the answers to the quizzes and announce the winners and finally conclude. So just so you know what's up tonight, that's the program. So our first speaker tonight is Leonard Burtscher. He is a staff scientist here at the observatory in Leiden. And this lovely image of the screen of him is taken at his favorite wavelength range, the thermal infrared. That's the area that he works in. So Leo got his PhD at Max Planck Institute for Astronomy in Heidelberg. He works a lot on the mid-infrared. As you can tell, he likes that wavelength range. But looking at active galactic nuclei, so black holes and galaxies. He did a postdoc in both science and technical work at Max Planck Institute for Extraterrestrial Physics in Garching in Munich. And since 2017, he's been here in Leiden, and he works as a calibration scientist for the extremely large telescope, specifically the METIS instrument. Leo is passionate about science education and outreach, and since I've known him, I can tell you that that's certainly true. He's recently started a project, co-leading a project that is a worldwide group of astronomers that are trying to use the astronomical perspective to convey a feeling of global citizenship. And maybe he might tell you a bit more about this. But his talk will outline some of the astronomical factors that influence climate change on Earth. And maybe this is giving the game away already. He'll reveal that none of these are responsible for the current climate crisis. And a fun fact about Leo is that he recently starred or played in a commercial where he acted as an astronomer. So Leo, you might have to tell us what was this commercial advertising, or maybe that'll just be product placement, so you can't.
I won't name the company.
Sorry, what was that?
I won't name the company, but it was about a heating system.
Oh, more thermal infrared. Okay.
A difficult link. They have an advertisement campaign showing people who work outdoors, and then they come home into their nicely heated homes, and they wanted to emphasize how things can also be, let's say, environmental friendly in terms of heating, using heating pumps and these sort of systems. Mm-hmm. And so they search for an astronomer who cares about Earth as well.
Yeah. And that would be you. So over to you, Leo, for your talk.
All right, well, let me start my screen sharing then. Okay. All right, so welcome everyone. Good evening. Happy to, well, be here online with you. Unfortunately, not see you. That would be even nicer, but still happy to know that you're all there. So this talk will be indeed about the climate crisis from an astronomical perspective. And since Wendy already introduced me, I don't have to say anything more about myself here and can jump directly to the talk. As Wendy has also already said, which is perfectly fine, I want to convey in this talk what makes Earth special in an astronomical context and what factors influence the climate on Earth. But I also want to take you away right at the beginning and several times in between that this is not meant as a talk to say, oh, climate change isn't real or we're not the ones who cause it, but just to outline what is the astronomical part and what is the human part. So this is kind of a spoiler in advance, but I feel it's important. Otherwise, it might lead to some wrong impressions. All right, so what is it that I'm going to talk about? So first, our place in the universe. What are habitable zones? Why are we in a special place, in a special galaxy? And why are we in a special place within our solar system? And then more specifically about our solar system, I'm going to talk about the sun and solar activity, which is often cited as a cause for climate influence. And of course, the sun has a big influence on our climate. I will show what relation there might be with historic events in Earth's climate, both from the sun and also from our orbit around the sun. And then finally come to our own climate crisis, as I call it, which is happening really happening since about 50 years or so, and which has nothing to do with astronomy, really. But we'll come to that in a moment. All right. So habitable zones, you certainly have heard about this with all the exoplanet talks at Astronomy on Tap and elsewhere are in everyone's mouth. There is not just the circumstellar habitable zone that we'll touch in a minute, but there's also the concept, at least, of a galactic habitable zone. And the idea there is that not in every galaxy, and then not in every place in a galaxy, can intelligent, complex life evolve. And this is an important constraint, complex life, meaning life that is not just a few bacteria, perhaps, or perhaps that is already complex in this sense, but life that is composed of many organs, let's say, something like a human or an animal, that requires a long time for evolution, and therefore a long and steady environment to evolve. And so our galaxy is special in the sense that it is a relatively boring galaxy. It doesn't have a lot of nuclear activity. Yes, there is some, and you might have seen some really fancy images lately of stars circling around the black hole in our solar system, the black hole that we know the best of all, massive black holes, at least supermassive black holes, 4 million solar masses. And there is this one star called S2 that is circling around very, very, very quickly within 18 years or so. But this black hole in the center of our universe, where this laser, by the way, is pointing to on this image, it doesn't do a lot. It just sits there and it's relatively quiet. It might have done a little bit a few million years ago, but it's not producing massive jets or outbursts or things that could cause problems for life. Then another factor is that we're sitting roughly halfway between this center, where, while there isn't a very big, let's say not a very bad black hole, that's not a very scientific term, not a very active black hole is perhaps the term to use. It's still a region in the center where it's very dense, where you have lots of stars and lots of gas, and so lots of collisions, lots of gas collisions and lots of close encounters. So that might still be not a region where complex life has a very good time evolving. And very far out, it's again difficult to evolve something like, or to first create planets and then evolve life on these planets, because very far out there are too few what astronomers call metals. So things like carbon or silicon that are needed to build rocky planets. And then finally, also our direct solar neighborhood, the so-called local bubble, is relatively quiet, at least over the last few million years. And then there is the concept of the circumstellar habitable zone. And that is now really what makes Earth special within our solar system. And there you have probably all seen this concept that says, okay, if you're too close to the star, water boils away and you cannot have any liquid water on the surface. And if you're too far away, you get icy planets. So there is this region in between, which is classically called the habitable zone, where water can be liquid on the surface. And so life as we know it, that's the usual catchphrase, can develop and exist. And that in our solar system, you see, is in principle true for Venus. But of course, in Venus, the climate is crazy. It's true for Earth and for Mars in principle, but Mars, as you know, is too light to have a proper atmosphere. So it's a planet with almost no atmosphere, and therefore also not suitable, at least at the moment, to live on. There is also a number of other factors that make our solar system special. One is that our sun is actually, again, a very quiet star, even for a sun-like star. So stars that have the same mass as our sun are usually more active. They have more flares and more variability in their flux and so on. And our sun is, again, of the more boring sort, and that's good for us because it means that things are stable and calm, and we can evolve quite nicely. And further factors are that we have a moon that might stabilize Earth orbit, and Jupiter takes away some impacts. All right, so now let's have a look at solar activity. As you might know, the sun shows a cycle of 11 years that you can see here on the axis. We count here the number of sunspots that you will not see at the moment if you look at the sun, of course, only with protective glasses, please, because at the moment the sun is very inactive. It doesn't show a lot of sunspots, but if you look over the years, you see that within every 11 years, you get these cycles of a few more of these spots and a few less of these spots. And this 11-year cycle of the sun is very well known. It can be recorded back for a long time. Actually, Galileo started to look at these sunspots, and since then we have these sunspot numbers, and we can use these sunspot numbers to essentially build a proxy, a measurement that we cannot get directly for how active was the sun in the past. And we can try to correlate this with events that happened on Earth to see what is the impact of the sun on the Earth. And indeed, if we look back into the year 1608, or that period, that was a period where there were relatively low temperatures, cold temperatures in Northern Europe. It was called the Little Ice Time, and Little Ice Age. And that's also the time when this really nice painting from Hendrik Averkamp was made, where you can see people ice skating on the canals, as the Dutch so love to do, but unfortunately cannot do anymore these days. And that is just a sign that at this time, the sun was particularly, or let's say the climate was particularly cold. And people can then try to combine this with solar activity. And this is now the solar activity over the last 1,000 years or so. This is now not reconstructed from the sunspots, but reconstructed using the 14C isotope of carbon. So the atom carbon has different variants of it, and C14 is a carbon that has 2 extra neutrons in it. That they don't change the chemical properties a lot, but they change the weight of the atom. And so this carbon is no, sorry, that is a different explanation. This the C14 is a radioactive isotope, of course, of carbon, and it can be used to you get the age of things by using C14, but it is also mostly created by cosmic rays, and cosmic rays again mostly come from our sun. So by looking at the activity of C14 over the history of time, you can again build such a proxy of the solar activity. And we see here that indeed around the year 1600, the solar activity was a little bit lower perhaps than the average of the last 1,000 years. And actually the region, the time of around 1700, has a funny name. It's called the Maunder minimum. And this is really the time when solar activity was relatively low and temperature on Earth was also relatively low. And although this would be a really nice link, and often people say, oh, that shows that the sun is influencing our climate, it's not really clear that that has been the case at this time, because there's also a number of other explanations that I will come to in a minute. For example, orbital cycles of the Earth that change volcanic activity, and also that the climate just changes inherently. It's a complex system, and it can just change from time to time. And certainly if we look at nowadays curves, so the last 100 years or so, where we definitely have direct measurements of both the solar activity and also the global average temperature, because we've used thermostats for a long time. You can see here in yellow the solar activity, and you can see the 11-year cycle plotted over it. And then if you look at the average, you see that it's, as we said, a fairly stable sun. So the activity of the sun changes less than 1 watt per square meter. It changed less than 1 watt per square meter over the last more than 100 years. So that's, yeah, you can say almost a calibration source, almost a very stable source that you can use as a trusted source. On the contrary, the temperature curve, as you know, is rising upwards very steeply since 50, 60 years or so. And it's not correlated at all with the solar activity. So the answer to this question, is it the sun's fault that our climate is heating up, is clearly no. There are some other factors that influence the climate on Earth. And this is where the explanation that I started before comes in. So this is, again, looking at a proxy, and it's a bit of a complicated plot, but bear with me. It's, I think, a very nice way to show or to try to understand how the climate history on Earth was. So this shows now another isotope. This is in this case not carbon, but oxygen. Again, oxygen normally has 16 atoms, and this specific one has 18. So this is now where the thing is a little bit heavier, and therefore it sinks down. It is more often found in ice, which is on the surface, rather than in water vapor in the air. And therefore, this relative frequency of this isotope is an indicator for the temperature, essentially, on Earth. And this isotope can be found through ice core drillings over a long time back into Earth history. And you can find this period of, or you can find this curve of lasting 600,000 years back, and you can see how this isotope is going up and down. So the Earth temperature must have been going up and down. And we know this also from other indicators, that over the last 2 million years or so, there has been this cycle of ice ages coming every roughly 100,000 years. We're currently in a so-called interglacial between two ice ages. You can see it went up just before like 10,000 years ago or so. Next ice age would be in about 50,000 years if we don't add too much CO2. And if you look at this, you can see there is this clear peak in this Fourier diagram. Now, this is something for specialists, perhaps. You can see that every 100,000 years, roughly, there is this increase in activity this cycle of temperature changing up and down. All right, and there's a number of things that could cause that, and I have to be a bit quicker on this. So there is orbital eccentricity that changes changes in the eccentricity of the orbit of the Earth that could cause it in principle, that the Earth orbit is changing in this way. The actual tilt, so the thing that's causing seasons for us, that is also changing. It's 23.5 degrees at the moment, as you know, but it changes between 22 and 24.5 degrees. So that makes summers and winters either more or less extreme a little bit. And then there is some other factors, and I'd just like to point out this one. That's the inclination of the Earth orbit with respect to essentially Jupiter's orbit. And this particular inclination aspect might be quite important in changing Earth climate. And we'll come to this on this slide. In general, this whole scheme of Earth orbital variations possibly impacting the Earth climate are called Milankovitch cycles. And the idea is found by a guy called Milutin Milankovitch in the early 20th century. The idea is that these variations, these regular variations of ice ages and warm periods, every 100,000 years, an ice age, and then a warm period again, they might be related to effects in the orbit of the Earth. And if you look at all sorts of variations that happen in the Earth orbit, the one that has the same periodicity is actually the inclination. So the inclination of the Earth orbit with respect to the other planets, which is tiny, but it is enough that it changes Earth orbit in a way that sometimes it flies through the plane of the other planets, and sometimes it doesn't. I see that I have to speed up here a little bit. And the reason for why this change might come across is that if Earth is hitting the plane of all the major planets, then there might be a large amount of cometary dust there, which then hit the Earth atmosphere and cause some increased darkening, let's say, in the Earth atmosphere, so like a volcanic eruption, and that might then trigger an ice age. All right, so we've covered a few effects that might impact, or that probably do impact Earth's climate, but, and this is really the important point now, these are all effects that happen on really long timescales. The solar changes happen on shorter timescales, but there is no clear relation yet that they really affect the Earth's climate. There's some indications like this little ice age between 16 and 1800, but it's not certainly not clear, or actually it's clear that it does not affect, it's not the main reason for the temperature variation that we see right now. And so this is what we can produce these days, or what our colleagues, the climate researchers, produce these days. They produce curves that show all the natural effects. It's the blue curve that includes the solar forcing, it's called, so the solar irradiation. And then you can compare this to the observed temperature curves, and they all agree very well with each other, although they're competing groups. And you can see there is a clear deviation from what is expected with natural curves from what we actually observe. There are two other visualizations that I'd like to show you on this. One is about the CO2 concentration that you might have seen before, but this is really, again, a reconstruction over many, many thousands of years. You can see these ice age cycles that also affect the CO2 in the Earth's atmosphere. And you can see what's happening in the last 50 years or so. And it's an increase that is so steep that you can almost not see it here. But there is fortunately a much nicer representation, and that is this movie. I hope this comes across in this online version here, where you can see how our global carbon bucket is filling up with gases emitted by the various regions. And it's getting faster and faster as economy is going faster and faster. And in 2019, only this little bit of carbon bucket was left that we are allowed to fill to reach the Paris Agreement goals of heating up not more than 1.5 or 2 degrees. So what this tells us is we need to act really now. And this brings us really almost to the next talk, namely with the question, what can astronomy do to solve the climate crisis? Well, I hope I could convince you that astronomers or the astronomical environment determines the habitability of planets. We live in a really special spot in the universe, and we are on a very special planet. There is no planet B yet, at least. We don't know any other planet that's as nice as the Earth. But also these astronomical effects that we see happen on really large timescales, on long timescales, and they are not responsible for the global heating that we observe in the last 50 years. Apologies. Changes of our astronomical environment, like the solar irradiation, are actually included in climate models, and they are not sufficient to explain this warming that we see. So this is really us causing it, and we need to get our act together as humans to change this. And in the last half minute, I just want to say, astronomy is also a discipline that actually emits quite a lot of carbon dioxide. We can go into the discussion about this if you like. I have even some backup slides on this later. And we need to reduce that as well, and we're actually working on this. But then there is this other aspect of astronomy that is even stronger, that is astronomy showing us the wonders of the universe, the special location of the Earth, that I think can really be used to convince people that we need to protect our only home. And this leads us to Michelle's talk after the quiz break. Thank you.
Thank you very much, Leonard. That was a very interesting talk. We have a couple of questions here for you. So Rocco is asking, in the 11-year solar cycle slide, it was clear that the 11-year peak is decreasing in the last about 50 years. Does it mean that we are going for another possible ice age? And is it a cycle of ice ages?
So the cycle of ice ages has been about every 100,000 years over the last several million years. It's not entirely clear why that is, but the expectation is that it's indeed from variations in the inclination of the Earth orbit compared to the inclination, or compared to the plane of Jupiter's rotation. So the sun is not causing the ice ages. And indeed, the next ice age would be expected in about 50,000 years. But as far as I know, with the current CO2 levels that we have, no one expects an ice age to come anytime soon.
Okay. If it was possible, what astronomical effects could counterpart the climate change? So you were saying how the sun is not really enough to account for the change that we're seeing, but is there anything that could be?
Yeah, I mean, of course, the sun is the major source of energy input on the Earth. There's a little bit of Earth heating, so to say, or the radioactive decay from the Earth core as well. But most of it, of course, is from the sun. And there are some wild theories, as you may know, to put some particles between us and the sun, some, let's say, an armada of small satellites to reflect a part of the sun's light to reduce the solar irradiation. That may be necessary in the really last resort. I hope not. It would be, of course, extremely difficult. It's also not clear if it would really work. Some people also say this might be, adding reflective particles to the Earth's atmosphere. which might be simpler than having lots of satellites. But that would, of course, affect us astronomers peering from the ground massively. So, okay, if it helps the rest of humanity, we probably won't complain, but still, it's just showing you that this would be changes on a massive system-wide level that we don't really want to experiment with, because we only have this one planet to experiment with, so we don't really want to experiment with it.
Okay. There's a couple of people that would like that are asking to see the extra slides that you have.
All right. So let me quickly fire this up. All right, these are 5 extra slides, and they provide another direct link to Michele's talk. So let me show this to you. This is about our own carbon footprint as astronomers. I'm always looking to my second screen here to see if everything's displayed correctly. As many of you may know, astronomers, of course, are jetting around the world, not these days, but usually quite a bit for conferences, for observing trips, for all sorts of things. And that produces quite a lot of carbon emissions. 2 institutes, as far as I know, have done a sort of carbon budget or carbon audit so far, last year, both. One of them was the Max Planck Institute for Astronomy in Heidelberg, where I did my PhD, and still know a couple of people. And they compiled the major sources of emission for 2018 of their institute. So MPIA is similar to the Leiden Observatory, I think. So you could, not quite sure about the number of people. I think MPIA has 300 employees. I think we might be a little bit bigger, but it's quite similar in terms of mix of research and instrument building. And so I think it can be seen as a proxy, if you want, for Leiden. And from these numbers here, you can see that flying is actually almost half of the emissions that this institute produced, with another 30% almost from electricity. And the electricity is only partly what is used on site, so to power your own computer and the light and so on that you always turn off when you leave your building, etc. All nice and good. But more electricity is actually used off-site at supercomputing centers. And this is a major source of emission for this institute in particular, because Germany is, as you know, burning coal quite a lot, like the Netherlands as well, to produce, and many countries, to produce electricity. So that's not very good. Yeah, this can be converted to gigatons or tons per employee and compared to various other people. But perhaps the other interesting part is to look at ESO, the European Southern Observatory, the biggest, I think, observatory on Earth, at least in terms of number of telescopes that they control, and also our major contact point for both as astronomers and instrument builders. They have their headquarters in Garching, close to Munich, and operate the telescopes in Chile, both the VLT and ALMA and La Silla, and soon the ELT, so a number of telescopes. And they had their carbon footprint assessed by a company called Carbone 4, a French company. And they did this in a very comprehensive way. And it actually shows how complicated this is, because you need to include not just the emissions from your own company, that's called scope 1 and 2, but also from what products you're using and what products that you produce will eventually, what kind of emissions they will produce. And if you take this all into account, this is the grand total that they found. So 28 kilotons of CO2 emissions. To give another number in context, the carbon budget, the bucket that I showed before for the whole Earth, is something like 600 gigatons as of 1st of January 2019, that we as humanity are allowed to emit. And that shows you already that this is not a negligible number. I mean, in astronomical terms, where we think 10% is a small error bar, yes, but in overall terms, this is actually quite something compared to our global carbon budget. So this is already quite a bit. And the other interesting thing you can see here is that for ESO, energy is actually the biggest polluter, and that's to a large part actually from Paranal, so from the telescopes in Chile. Because they are at the remote site and they use gas to produce electricity, and that is again not very climate friendly. and some more is from purchases and travels. Yeah, I think I'll stop here just to say that this is complicated by itself to produce such a carbon footprint calculation. So yeah, so we astronomers produce quite a lot of carbon dioxide, and we need to reduce this ourselves. That's certainly our own ambition as well.
Great, thank you very much. So there's a few more questions, but we've run out of time. So we will we'll move on to the games now, and then maybe if we have some time, we can discuss them at the end.
All right.
Thank you very much. So Stella.
Hi, and welcome to the games. Today we have two different games for you. The first one is climate change on Earth as seen from space, and the second one is climate on other solar system bodies. Like last time, the questions can be answered in Google Forms, the link of which is given here and should be also given right now in the chat. So if you follow that link, you can have to fill in your team name, your email, if you want to have a prize, if you end up winning, and yeah, move to the next section. I'll give you a bit of time to go to the correct site. So the first game, as I said, is climate change on Earth as seen from space. So this game will involve data from Earth observing satellites, and usually involves some kind of comparison of before and after images. Okay, the first question: what's the cause of the reduction in air pollution as shown in these images? A, strong winds. B, International Earth Day. C, coronavirus-related lockdown. D, upsurge in the usage of green energy, or nothing else. Two, how long did it take for this tree cover in pink to be lost in the Amazon rainforest? A, 42 years, B, 35 years, C, 17 years, or D, 6 years? By the way, I will rotate through these questions one more time, so you don't have to hurry too much right now. 3, what creates these bright blue swirls in the sea that you see on the right-hand side image? A, a chemical spill. B, underwater volcanic activity. C, fresh water from a melting ice cap. Or D, plankton. I'm going to show a video now, but the question is, the first image was taken on 28th of June. How many days later was the second image taken? And you can see it switching back and forth in a bit. As said in the title, these images are from the heat wave that was hit Europe in 2018, if that's enough of a hint. Okay, what is the length of the iceberg that is breaking loose in this GIF on the right-hand side? Is it A, 160 meters, B, 1,600 meters, C, 16 kilometers, D, 160 kilometers? How long did it take for vegetation to change this much, as seen from the top panel compared to the bottom one? A, 21 years, B, 5 years, C, 6 months, or D, 3 months? So question number 7, what do you see happening in these images? So the left panel compared to the right one. A, dying fish. B, plastic pollution. C, coral bleaching. Or D, temperature change. Question 8. How long did it take for the Azuelo Lake in Chile to dry up as shown in the image? A, 3 years. B, 10 years. C, 16 years. Or D, 25 years. Nine. What are these colorful patches appearing in this time lapse of the satellite images of the Netherlands? Maybe as a hint, there's a time for each of the images on the right corner. A, tulip fields blooming. B, King's Day celebrations. C, fruit and vegetables ripening. D, chemical leakage into water reservoirs. And as a conclusion for our first game, we have a tiebreaker question. What is the number of active satellites currently orbiting Earth? Before I rotate through these questions again, I will do the second game, but you can easily go back and forth between the sections in the Google form. At least it should be very easily. So don't worry, if you go to the next section, you can go back again, as long as you don't submit to me. So the second game, it's called Climate on Other Solar System Bodies. And question 1. What is the difference in the temperature of Mercury's surface when it's facing towards and away from the sun? A, 250 degrees Celsius. B, 485 degrees Celsius. C, 610 degrees Celsius. Or D, 850 degrees Celsius. Number 2. Which world in our solar system has the most water? A, Ganymede. B, Enceladus. C, Earth. Or D, Europa. Number 3. How many hours of continuous sunlight would you get in Uranus during summertime? A, 17 hours. B, 3 days. C, 21 years. Or D, none. Number 4. What speeds can winds reach in Neptune? A, 400 kilometers per second. B, 1,000 kilometers per second. Or C, 2,000 kilometers per second. Five. In which other solar system bodies have active eruptions been directly observed? A, Io, Enceladus, and Europa. B, Io, Enceladus, and Triton. Or C, Io, Venus, and Europa. 6. Roughly how much more carbon dioxide does Venus have in its atmosphere compared to Earth? A, 5,000 times more, B, 15,000 times more, C, 150,000 times more, or D, 500,000 times more. Seven. If you were standing on Mars' equator at noon, what would be the temperature difference between your feet and your head? A, less than 5 degrees Celsius, B, about 7 degrees Celsius, C, about 10 degrees Celsius, or D, more than 15 degrees Celsius. Which planet in the solar system has the biggest ocean? A, Earth, B, Jupiter, C, Venus, or D, Neptune? Nine. If the atmospheric pressure on the Earth is 1 atmosphere at sea level, what is it on Venus? A, 13 atmospheres, B, 48 atmospheres, C, 92 atmospheres, or D, 147 atmospheres. Which planet holds the record for the largest known storm? A, Earth, B, Saturn, C, Jupiter, or D, Neptune? And our last question. Which planet other than Earth is currently tectonically active? A, Mercury, B, Venus, or C, Mars? Okay, I will rotate through the questions one more time so you can go back to the section. Start from here. And here we are back at our last question. So I will give about 5 more minutes before I close the quiz. So feel free to still think about some of the questions. But otherwise, I think we are about to go on break.
Okay, so welcome back. Thank you everybody who's participated in the game. I hope you had fun doing it. Some of those questions were tricky, even to me. But we're going to continue now with the second talk. And then after the second talk, we'll review the answers to the questions so you can see what you didn't get right or maybe why. So without further ado, our next speaker is Michelle Willebrands. And before I say anything else, here is an amazing picture of Michelle and her fun fact that she sent us. It's not upside down, it's the right way up. She loves, when she's not doing astronomy related things, to be soaring through the sky doing aerial acrobatics. And that is some pretty amazing gravity defying feats right there, Michelle. But some more information and background about Michelle is that she is an astronomer turned a science communicator. She works here at Leiden University, and she's got master's degrees in both astronomy and science communication. And currently she coordinates the International Astronomical Union's regional office for astronomy for development. So the IAU regional office for AoD in short. But her work is all about realizing the potential of astronomy, including its skilled people who work within astronomy and the infrastructure that we use, really using this all to contribute towards social economic development and towards the United Nations Sustainable Development Goals. In short, this is using astronomy to make the world a better place. And her talk tonight will discuss some of the role of astronomy in the global climate change challenge. In particular, she will highlight the Pale Blue Dot project. So over to you, Michelle.
All right, thank you. Welcome back, everyone. I hope you enjoyed your break and that you have your beer filled up again. Let me see if we can start these slides. So now that Leo has told you all about the scientific angle that astronomy can offer to the climate change discussion down on Earth, there's some more that astronomy has to offer in the discussion. And I want to talk a bit more about this philosophical perspective that astronomy offers on our home planet. I want to tell you a bit more about the story of the Pale Blue Dot. And this story starts with a spacecraft, Voyager 1, that started decades ago on a journey away from Earth, way into interstellar space. That journey started in 1977. And it was quite an interesting mission, scientifically speaking. It was going all the way to the edge of the solar system and was going to be the first one to provide detailed images of our two largest planets and their major moons. So that's Saturn and Jupiter. This is the track that the Voyager 1 and its sort of sister spacecraft of Voyager 2 were planning. So it started in 1977. And then 2 years later, it passed the first large object that it was targeting, Jupiter. And only a year after that, it passed Saturn already. Right about that time, there was one of the lead scientists of this mission, Carl Sagan, proposed to turn around the camera and instead of looking out into outer space, look back at Earth and take a photo to show the perspective that astronomy has. However, it was refused back then. And this was not only because there would not have been any scientific interest in a photo like that, it would not provide any detail of Earth that we could study as scientists, but moreover, there was a potential that a photo like that could damage the cameras on board. The sunlight would be in the frame, and that huge light source could damage the cameras for good, making it inoperable. So Voyager 1 continued its journey. It moved out and away from Earth until it passed Neptune's orbit. That happened all the way years later in '89. So Carl Sagan tried again. he never forgot about this idea of the photo, and there were lots of people supporting him, thinking it was a great idea. So they tried again. And then in 1990, on Valentine's Day, it was taken. They accepted to take this photo, even though there was no scientific merit, and look back at our solar system planets. Now, these are the photos that they took. They didn't only look back at Earth, they tried to take this whole portrait of our solar system family, and trying to target all the planets that were possible to image here. Some of them were, I think Mars here is behind the sun, and others were too small. So these tiny dots all were a result of one scientist who had a crazy idea that astronomy could not only provide these curiosity-related scientific facts, but also a perspective that could prove very valuable. So that resulted in this photo. It was the photo of the first slide, but as you can see, this is a slightly different one. Just this year, NASA has revisited the data from the original photo, but updated it with modern techniques to get this improved version. And you can see this tiny dot here. And this dot is not even a pixel, it's less than a dot, really. And yet this is a very special image. First of all, you can see that it's right in what is almost looks like this ray of sunlight. And these rays, they are not real. These are reflections of sunlight in the camera, but somehow it seems to shine down on Earth, becoming a very special point in this photo. And the second thing, of course, is that this dot is blue. And a lot of people think that this blue color is caused by the oceans of Earth, causing the blue color. But that is not actually the case. It contributes a little bit, but it's mainly caused by Rayleigh scattering. And Rayleigh scattering simply means that all wavelengths can go through the atmosphere of Earth, and the red wavelengths, the longer wavelengths, can just pass through without any problems. But the shorter ones, blue light, actually reflects off of it. It scatters. And therefore, that blue light reaches the camera, making our home planet seem blue. So this photo was one of the last things that Voyager 1 produced. And then after that, it shut down forever. Voyager 1 is now still floating away from Earth. And in 2012, it entered interstellar space, being now the most distant human-made object ever around, which is quite an astonishing perspective. And this is also something that made this photo special. I think this is what makes it memorable. And Carl Sagan, the scientist who proposed to make the photo, wrote a whole book about it. And this quote, I think, is known by so many people, but it is very powerful. Look again at that dot. That's here, that's home. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. So it's not the knowledge about the stars, about our universe, that made the impact. It's looking back at our own Earth, looking back home. Of course, that's not the only photo that has done that. There's many, many photos, all worth highlighting, but I'm only going to show two. The first one is Earthrise, which is quite special because it's, I think, the first time that most people were able to see Earth from the outside, seeing all of Earth in this vastness of black space. This photo was made possible through Apollo 8, which was the first manned mission to the moon. And this photo is actually not upside down. This is intentional. This is the way that the astronauts saw Earth rising over the horizon of the moon. And as many of you might know, astronauts often report this cognitive shift of awareness when they first see the Earth from the outside. And this shift is called the overview effect. And this simply means that when astronauts observe the Earth like they see in this image, they suddenly realize that all of our individual problems don't really matter all that much. When you see Earth from the outside, you see that there are no national boundaries. Those are man-made, and they don't have any real meaning behind them. You also see that Earth is vulnerable. You see that it's only protected from space by a very tiny layer of atmosphere. And that means that we need to protect this Earth. We need to protect this home to be able to keep living on it. And this photo has been called the most influential environmental photograph ever taken, which I think many can understand why. The second photo that I'd like to highlight is this one, simply because it's so stunningly beautiful. And it's often called the day the Earth smiled. Produced by Cassini-Huygens not even that long ago. And what is special about this photo is that people were already warned in advance that it would be taken. Often these photos are produced, but no one knows about it until they're published. But for this one, everyone was informed before. It was announced. And people were asked at the moment of the photo picture to look up at the sky all together and smile in celebration. Now, what the message of these photos, I think, is all the same. And we often call this the pale blue dot message. And these photos show us what's at stake. They show us our home and the fact that it's the only one, an inevitable fact that we need to protect it. And it also shows us that we can stand together, we can unite, and we can protect it. The photo that you see here is one that is cast pretty much right after the Earthrise photo. After this photo, people suddenly realized this perspective. They realized that Earth is a very, very special place that we need to protect. And people went out on the streets and trying to create this message and spread the word. And after this, now every year we celebrate Earth Day. So it is this that I think astronomy can offer to the climate change discussion. It's the cosmic perspective that astronomers have. It's the perspective from going to the small things that are so known to you and that you all love, and then zooming out. The images that you see here are called The Powers of 10, and I won't go into detail, but it's worth looking up. It's a movie that shows you that when you zoom out, you suddenly realize we are all part of the same Earth, and we are only a very tiny space in all of the universe. And this comes back to the idea of global citizenship. This is what astronomy can be used to promote. Global citizenship means that you feel not just a citizen of your own town, of your own family, of your own country perhaps, but feel that you are part of all of the Earth, that if something happens on the other side of it, that affects you too. And we know that this can be promoted through astronomy because astronomy creates this feeling of awe. And awe in its turn can also result in increased levels of empathy, resulting in global solidarity. So the way that UNESCO describes global citizenship, and the definition that we usually hold, is that you can empower people to assume an active role, both locally and globally, in building more peaceful, tolerant, inclusive, and secure societies. To get people to change their behaviors, to act on global challenges altogether. And this is something that astronomers are doing. We have this union of astronomers internationally, the IAU, and they have set up this flagship project celebrating our common humanity, celebrating that we are all here under the same sky. And the idea is to use the beauty and the enormity of the universe to stimulate this sense of global citizenship, to stimulate a sense of solidarity and tolerance towards other cultures in all parts of the world. And this in turn can contribute to development in general, to the United Nations Sustainable Development Goals, because this mindset of feeling part of all of the world is a necessary beginning to be able to act on global challenges. So to tell you a little bit more about what has been happening so far in the astronomy community, besides, of course, all the amazing, interesting facts that Leo has told you about the carbon footprint that we have, there's also this more intangible aspect that astronomy has been exploiting. We have organized activities across the world in February when this pale blue dot photo had its 30th anniversary. We had a symposium in Leiden, but all around the world there were activities using astronomy to start this discussion about global citizenship and about climate change and how important it is that we start acting now. And we also intend to set this up as a global project, an education project for young children, where the goal is threefold. It is about promoting this global citizenship and about raising awareness and moreover action on climate change. It's about educating the next generation of children so that they are prepared to tackle a lot of these global challenges that we all face. So there's actually quite a lot that astronomers can do. And besides these global efforts, these education efforts that are coordinated on very large scales, every astronomer can contribute to this. And Astronomers for Planet Earth is a group of astronomers that have been doing this, that are gathering all the information and all the passionate people to promote and be ambassadors for this aspect. And Leo and I are both part of that, and you can follow them if you would like to hear more about these topics in the future. But what I think is important is to realize that every individual can take part in this change. All these global challenges that are so complex and complicated need to be tackled at every level, including the individual one. And every astronomer can highlight sustainability and climate in their talks, whether it is through the scientific facts that you can relate to exoplanets or science weather or space weather or all of that, or just through trying to promote this mindset within your own community. And I think every astronomer should also try to raise this awareness at their own institute. You can try to at least create awareness, if not try to go for institutional change. We all can try to do this. And I think most of all try to fly less to conferences. As Leo explained, for a lot of institutes, this is the main contributor to climate change that astronomers have, and this footprint is not negligible. I know that Leo has actually stopped flying as much as he can, and last year he didn't take a single flight. I have, but still we try to be conscious about the decisions that we make, and also try to remember that astronomy, even though only based on curiosity, has a lot of potential for contributing to the climate change discussion. Because we have this perspective. We can see Earth from outside. And if you just realize that that is our home, there's a lot that everyone can do. Thank you.
Thank you very much, Michelle, for a great talk. We have a couple of questions for you. There's one about the photo from Saturn. Which side of the Earth was facing Saturn for everyone to smile for the camera?
Let's see. Can you repeat the question?
Which side of the Earth was facing Saturn for everyone?
I am not sure. Technically, you're right. Half of the people on Earth would not have been smiling actually at the camera. I'm not sure.
What age of children do you want to target for the education programs? And how early do you think that we can start to teach them that they live on the pale blue dot?
So I think choosing an age group is difficult, because in the end, you want to reach everyone with this message. Every age group can learn from this, whether it is children or adults. We can all still take away from this message. We decided to target children quite young, into primary ages, or the end of primary school, simply because we think that's when their value systems are forming. That's when you can influence the way that they see the world around them and try to instigate this change of behavior. You know, when you're learning, you first understand the facts, the scientific facts, but that alone is not enough to change the way that you behave. You then sort of go into this socio-emotional way of learning. You need to feel that it's relevant for you, and that is where global citizenship sort of comes in. You need to feel and emote that this matters to you. And only then you can really try and change behaviors. So we try to target everyone if possible. That is certainly what the IAU is doing with this flagship. But as here in Leiden, we go for younger children, say age 9-ish.
Do you think that astronomers currently do enough to engage the public and deliver results just for fun, like Carl Sagan did with his photo?
I think a lot of astronomers really try their best. I think more and more people realize that we all have our part to play in this discussion, but still there's of course always plenty of people who have not thought about it yet, and that still maybe feel this is a discussion far from their home. So in the end, there's always more that can be done. I think we should applaud all those people that are trying their best and spending all their time on promoting this. But yet there's always more. There's always more we can do.
Regarding the recent, the current situation of not being able to travel and fly, has this changed the perception of how necessary face-to-face conferences are? And do you think it will cause a change that will last?
It has definitely changed the perspective of a lot of people. And we have started these discussions a couple months before this pandemic happened, already sort of lining out what the benefits would be, but it was all theoretical. And now everyone is forced to work from home. And of course, there were some drawbacks in the beginning, not understanding the technology and maybe feeling that you don't have the same way of interacting. But then there's all the benefits. There's simply the fact that we are more efficient communicating online in many meetings. But I think the very most important factor is that we're more inclusive. Now that we are organizing a lot of our conferences online, suddenly all those people who normally can't join because they can't travel can be there. Whether that is for financial reasons, because they have care roles for their family, or due to disabilities, suddenly everyone can join. And I think that is extremely important. And of course, as becoming very clear from this talk, there's also the decrease in our footprint on Earth, which is, I think, something that we should always consider. So I sure hope that people will take this time to reflect and to think about what is really necessary. Of course, we all understand that some travels might still be necessary in the future, but certainly not all. It's not necessary to travel every week or every month by plane. So I hope that people will reflect and will consider their choices in the future.
There's we have time for one last question. Philip is asking, what optic effect causes this discontinuity in Saturn's rings?
The fact that it's different rings instead of sort of one major one. I
Yeah,
must admit that my astronomy background is already far in my in my past. So perhaps one of the astronomers can answer about this. As far as I'm aware, there's just not continuous lumps of dust and brick in all these different rings, and they reflect light differently.
Yeah, I believe there is a physical gap there. Yeah, no optic effect. Well, Michelle, thank you very much. And now we're done with the questions, and we'll go on to the answers for the quizzes.
Okay. The answers for the first game. The first question's answer is C, coronavirus-related lockdown. The data you see here shows that nitrogen dioxide levels fell about 45 to 50% during lockdown compared to the same time period of the year before. And although weather does have an impact on nitrogen dioxide levels, this contribution has been minimized by averaging the data over a whole month. And it's estimated that the weather-related uncertainty is about 15%, as seen on the right-hand side values. 2, how long did it take for this tree cover to be lost? And the answer is C, 17 years. So most of this tree cover loss is due to deforestation, but some is also due to fires and sustainable forestry operations. These bright blue swirls are caused by plankton. These are microscopic marine plants that drift near the surface of the sea. They play an important role in the climate of our planet because they absorb carbon dioxide during the process of photosynthesis, exactly like terrestrial plants do. And although most of, sorry guys, emergency with a cat. Although most types of plankton cannot be seen by naked eye, the chlorophyll they use for photosynthesis tints the color of the sea blue, light blue, and this makes them visible from space. Yeah, so this the difference between these pictures is indeed 27 days, so a bit less than a month, and the vegetation has gone from green to brown, as seen from this video. The length of this iceberg is 160 kilometers. It is, in fact, one of the largest icebergs on record to have calved from the ice shelf in Antarctica, and this took place in July 2017. So the vegetation took only 6 months to change this much because it is just seasonal variation you see here. The top one is from September 2007, and the bottom one is March 2008. These pictures show coral bleaching, and bleaching happens when algae living in the coral tissues is expelled. The leading cause for this is water temperatures rising by global warming. When the algae are expelled, the coral can die. And when this happens, obviously there's huge impacts on reef ecosystem, but also on coastal protection from storms and flooding, etc. So this lake only took 3 years to dry up, and the main cause for this was overconsumption of water. During this period, the agriculture in the area, which consists mainly of avocado growing, demanded a greater amount of water. But also this was made worse by the uncontrolled building of villas with large pools in the coast of this lake. This is obviously tulip fields blooming. Nice reddish and orange patches appearing in spring around this area of Netherlands. And the tiebreaker, it's 2,666 satellites currently active that orbit the Earth. All right, and now for the answers of the second game. So temperature variation in Mercury's surface is 610 degrees Celsius. Mercury is very close to the sun and has no substantial atmosphere. So these both contribute to the fact that the surface has a great temperature variation. The side closest to the sun can reach up to 427 degrees Celsius, while the night side can have down to 183 degrees Celsius. The answer to this question is Ganymede. Nearly half of Ganymede's total volume may be liquid water, which is about 6 more times the volume of Earth's oceans together. How many hours of continuous sunlight would you get in Uranus during summertime? And the answer is 21 years. Even though a day only lasts 17 hours, the fact that the planet rotates sideways means that in summer, the hemisphere facing the sun has 21 years of sunshine in a row. In Neptune, the answer is C. And as a comparison, the most powerful winds on Earth reach 400 kilometers per hour. Other solar system bodies that have active eruptions are Io, Enceladus, and Triton. Although, in case of Enceladus and Triton, they expel volatile gases instead of lava, so they would technically be called cryovolcanoes. So Venus has 150,000 times more carbon dioxide in its atmosphere than the Earth does. This amount of carbon dioxide causes a runaway greenhouse effect and a surface that is hot enough to melt lead. It's pretty crazy. So the correct answer to this question is D, more than 15 degrees Celsius. This is due to the thickness of Mars's atmosphere and a lack of oceans, which on Earth help regulate the temperatures. On Mars, the variations in temperatures can be very large, just depending on height from the surface. So the biggest ocean in the solar system is on Jupiter. Jupiter is mostly composed of hydrogen and helium, but way underneath the gaseous clouds that you see, the pressure rises to a point where this hydrogen must turn liquid. So computer models estimate that the depth of the ocean on Jupiter is around 40,000 kilometers. The correct answer here is 92 atmospheres. So a lot more than on Earth. The largest known storm. The correct answer, there's something gone wrong here, but the correct answer, I think there's Jupiter underneath here. The correct answer is Saturn. And while the most famous storms is in the solar system is clearly the Jupiter's red spot. But while the red spot can fit around 2 Earths, this storm that you see on the images on the right-hand side on Saturn can fit around 10 to 12 Earths. And this storm took place in December 2010 to August 2011. Mercury is another planet that's active, tectonically active. And the images you see here are obtained with NASA's Messenger spacecraft that reveal these small fault scraps shown on the right-hand side. And these scraps are believed to be geologically young, which means that Earth is not the only tectonically active planet in the solar system as previously thought. And this is it for the answers. And now I'm happy to announce the winners. All these people that you see, or teams that you see on the screen, got equal amounts of points, but Eva was the one that also was closest for the our tiebreaker question. So congratulations to Eva, and also for the runners-up doing really, really, really well. And back to you, Wendy.
So a big thank you to Stella and everybody in our games team for developing those questions. There are really some interesting ones. And Stella, I think your cats are now famous. They're getting a lot of attention too. Sorry, I never introduced them. And I think also tonight there's been two very interesting talks and fascinating about how our role of astronomy places us in the world and gives us a different perspective in understanding how we affect the world we live in and what we can do to make it a better place. And I really like the fact that tonight, even though we're doing this remotely, we actually have a much more international flavor in our audience. So I've seen people from the USA, from Pennsylvania, Cairo and Cape Town, both in different sides of Africa. And then more locally, just down the road here in Leiden, The Hague, Amsterdam. So welcome everybody and thank you for joining us from around the world. Just to advertise quickly, we will be back next month on the 29th of June with another live session on YouTube on a completely different topic. We'll be talking about gravitational lensing with Alessandra Sonnefeld and Kirsty Butler, two very different projects involving gravitational lensing. So I hope to see you then. And just briefly, there are a lot of other astronomy on taps in the world. And I think many of them are running events online. So take a look at astronomyontap.org. A very big thank you to our two speakers tonight for doing their talks and for doing them remotely. You will get Astronomy on Tap glasses if you don't already have them. I think, Leo, you said you've got one, but maybe you'll get another one once we're able to send these to you. And finally, this wouldn't happen without a large team of people, not just those of us you've seen tonight. So a very big thank you to everybody here, as well as the support of Leiden Observatory in doing this. Great, thank you all.